go. All right, so we just went over the homework for chapter 9. Variable midline, variable amplitude, stuff like that. Trig identities, fun stuff. All right, chapter 10 is really sort of review. 10.1 is composition of functions. 10.2 is using composition of functions to prove if you have an inverse function or not. And then 10.3 is just like a big mishmash of compositions. Okay, so let's talk about this. So what if I gave you the following functions? Let's say p of x is something, I don't know, sine of x plus 1. Sort of like what we just graphed, right? A midline with a constant midline other than 1, right? Y equals 1 is a midline. And q of x is x squared minus 3. And my question to you is, what is p of q of x? What does that mean again? We've done this. Take q and plug it into p. So take x squared minus 3 and plug it in place of x in where you see the sine of x, right? Okay, so let's write that. So that's going to be it's going to be p of x, which is sine of x plus 1, sine of stuff plus 1, plug in q of x, which is x squared minus 3. Okay, good. Now let me take that one step further. What's p of q of x? What's p of q of x? This is p of q of x. Take q and plug it into p. What's p of q of x? Take this result, this whole thing, and what? Plug that back into p again, right? Do it again. Okay. So if I want p of q of x, that means take p of q of x and plug it into p. But that is, what's p? Sine of stuff plus 1. But now what's the stuff? So now what's the stuff? I might need more room. Hang on. It's what we just got. The sine of x squared minus 3 plus 1. So that's compositions, right? P of q of x means take q of x, plug it into p. P of q of x means take p of q of x and plug it back into p. That's all it means. Okay. Not earth-shattering. We've done this. Alrighty. So let's go backwards. Can you decompose? Can you break it down backwards? What if f composed with g is e to the x squared plus 1? Can you go backwards and tell me who f was and who g was before they did the composition? Who's f, who's g? Can you break it up? Go backwards. So g is what? X squared plus 1, and f is? E to the x. Perfect. Very nice. You're so good at this. I don't deserve to be. Hang on. Some preacher comforts over here. Okay, so clearly what we're inputting is x squared plus 1 into e to the x. So g of x is x squared plus 1, and f of x is e to the x. So f of g of x means take x squared plus 1 and plug it into x into e to the x. What would g of f look like then? What if I said if this is g and this is f, what's g of f look like? I know what f of g looks like. I want to know what g of f looks like. Yeah. Well, think about it. If f of g means take g and plug it into the x of f of x, g of f means take f and plug it into the x in g of x, right? So what did you say it was? E to the 2x, right. There you go, right? Is that what you said? E to the 2x plus 1? Okay, let's do that. So in other words, so now I can say that g of f is take f, which is e to the x, plug it into g, so it's stuff squared plus 1, but the stuff is e to the x. Now you can leave it like that, but that is in fact e to the 2x plus 1, like you said. That's good. Now remember, that's important. Didn't we find somewhere back in chapter 3 or something that if f of g and g of f are equal, they're inverse functions? Are these equal? Is f of g the same thing as g of f? Is e to the x squared plus 1, the plus 1's in the exponent, the same thing as x to the e to the 2x, and the plus 1 is not in the exponent? They're not the same. In fact, more than that, if f of g and g of f are the same, and they reduce to just plain old x, we have an inverse function. F is the inverse of g and g is the inverse of f. That's section 10.2. Boy, we're so good at this stuff. Wow. But we're still in 10.1. Hang on. All right, what else can I do with this? All right, what if I said this instead? F What is it doing? There you go. Okay. So what if f of g of h of z is sine of ln of z all squared? So can you tell me who f is, who g is, and who h is? Who's the innermost function? Who's h? ln? So who's g? What are we plugging ln into? What does it say at the end? It says sine, where's my mouse? Sine squared of ln of z. What, is that messy? Hang on. Let me clean that up a little bit. Get rid of this ln. I don't like this ln. The sine squared of ln of z. So the innermost function is ln of z. That's h. I'm plugging ln of z into what? Into what? In sine squared, right. So who's f and who's g? Who's f and who's g? Is f sine or is g sine? How about that? Oh, sine times sine? I guess you could think of it that way. No, be careful, because it's, if you do f is sine and g is sine, you don't get f of g is not sine squared. It's f of g would be sine of sine. That's different. Yeah, close. That's different. I would say that g is sine and f is squaring it. Right, okay. So the innermost function h is the ln function. And then g, we plugged into that, is sine. And then f is what we did to the sine, square it. So you can compose, functions and functions and functions of functions. Doesn't it just have to be two functions? Yeah. Question? No? Okay. All right, so that's composing a whole ton of functions. All right, fine. What happened here? Good. All right. That's 10.1, believe it or not. All right, 10.2. How do you solve this? Say I tell you that the sine of x is 0.8. Now that's not a reference angle, right? You don't know an angle whose sine is 0.8. You know an angle whose sine is 1. You know an angle whose sine is 0. You know an angle whose sine is -1. You know an angle whose sine is rad 2 over 2. You know an angle whose sine is rad 3 over 2. Right? You know an angle whose sine is negative a half. Right? You know those. This is not one of them. So how to get rid of the sine? How to get x alone? Inverse function, right? Inverse sine. So if I take the arc sine of the sine of x, right? I have to take the arc sine of both sides. So the arc sine of one side equals the arc sine of the other side. And remember why it's called arc sine, because arc is fancy words for angle. All right, so this is really saying what's the angle whose sine is 0.8, and what does arc sine do to sine? What does a function, and what does an inverse function do to its function? Cancel. So all that's left is x is the angle whose sine is 0.8. And now that's an exact answer. That's the only way to write that answer exactly, because I think it's irrational. How do you get like a numerical estimate? How do you get like how big this number is? We're getting an angle, right? So it's going to be something between 0 and 360 degrees if you're in degree mode, or 0 and 2 pi if you're in radian mode. How do you get it? What do you do? Calculate, right? Okay, so x is approximately, let's find out. Ask Ziggy. All right, Ziggy, so let's see. Now, what second quit to get the home screen mode? What mode am I in? I'm in radian mode, right? So I would do second sine is arc sine of 0.8 is 0.927-ish in radians, okay? So I'm going to write 927-ish, put a little decimal here. Okay, so that's what we use inverse functions for, right? Okay. To solve equations. So how do you get inverse functions? Let's say I gave you this function. What if b as a function of t is, well, let's write it here, is 500 times 1.04 to the t. Does that sound familiar? What do you think b stands for and t stands for? Does that look familiar at all? 1 plus 0.04? How about that? Yeah. The balance in your bank account. And t is the time in years. This is simple interest, getting 4% interest every year, right? The 1 plus r thing. Okay. What if I wanted to invert that? How do you invert that? That's b as a function of t. I don't want that. I want f as the inverse function of b. How do we invert it? Now remember, inverse functions, all they do is they take the domain and swap it with the range. Here the domain is the t's, and here the range is the b's. What if you swap them and get t alone? How do you get t alone? Huh? I can't hear you. B what? What I'm saying is, what's the first step of getting t alone? Divide by. Okay, divide by 500. Okay, good. So let's do that. So b over 500 equals 1.04 to the t. There's a point there. And that's a messy 4. All right, next what do you want to do? How to get exponents out of, how do you get variables out of exponents? You log, right? Now, does it matter which log? Doesn't really. How about we use ln? I don't care. Doesn't really matter. I'm just going to use ln for fun. So ln both sides. So you get the ln of b over 500 equals what then? What would you? How does this reduce? Why is this good? T ln of 1.04. By the way, don't forget that the test on Friday, which is Thursday, includes everything in chapters 9, 10, 11, plus stuff from previous chapters, plus what wasn't on the last test. It should have been polar. So review 8.5 polar. Okay? Just reminding you. Polar graphs, polar coordinates. Not complex. Complex I'm going to throw on the last test. All right, so one more step to get T alone. What do? Divide, right. So T is the ln, or whatever log you chose, of b over 500, all divided by the ln of 1.04. And now notice what you got. What you got was, instead of b is a function of t, you now have t is the inverse function b, is what we just figured out. Okay? So what good is that? Well, if I plug in here years and I get money, right? What happens here? I'm plugging in money and I'm going to get years. So here the question is, if I want to know in 10 years how much money I get, I plug in 10, right? Here the question is, if I plug in B is $5,000, how long does it take, right? All right, so just for fun, let's do that on a Ziggy. Let's calculate this. What if I want to get 5,000 bucks? Okay, so I'm going to get the ln of 5,000 over 500 divided by the ln of 1.04. Let's see what that is. What is the ln of 5,000, just to be silly, divided by 500, in other words, ln of 10, divided by the ln of 1.04 is going to be 58 some odd years. So, if I go back here and I plug in 58 years, I should get about 5,000 bucks, right? Whoops. Now notice, it's not 58. It's 58.7 something. It's more than 58. So if I go back here and I plug in 58, I should get a little less than 5,000, let's say. All right, let's do that. Let's plug in. You know what? How about we plug in the answer we got into here? If we plug in the answer that we got, we should get 5,000, right? All right, so let's do that. So let's take that answer and plug it into here. It's 500 times 1.04 to the second answer key, 5,000 bucks. Or if you want to just put in 58 years, you would get less than 5,000. And if you put in, say, I don't know, 59 years, you should get a little more than 5,000. So, makes sense. Inverses just swap the domain and the range. That's all it is. Okay, good. All right, so how about this? What if I gave you y equals 3x over 2x plus 1? And what I want is the inverse of that function. So if this is y equals f of x, I'm asking what's x equals f inverse of y? Can you get me f inverse of y? How do you do that? Solve for x, right, that's all. All right, so let's do that. You know, I'm going to just get rid of that. So first step in solving for x would be what? Huh? Multiply by what then? He said specific. Be specific. What am I multiplying by? Huh? 2x plus 1? Okay. That's technically not multiplying by the reciprocal. It's just cross multiplying. Alrighty. So if I have a y here, technically it's over 1, so I can cross multiply. One fraction equals one fraction. So you get y times 2x plus 1 equals 1 times, let's be ridiculous, 1 times 3x. Okay, there you go. But again, I'm trying to get x alone, so what do you got to do? Divide by 3? That's going to muddy the water. I wouldn't do that yet. No. What's your favorite D word? Distribute. What if I distribute? Look, what I need to do is I got to get all the x's on one side to solve for it, right? I got x's here and I got x's here, but it's complicated because I got a y in front. What if I distribute? I get 2xy plus y equals 3x. So to get the x's alone, I got to get the x's on one side and everything else on the other side. So what do you do now? Not divide. Subtract what? Subtract 2xy. You want to do it that way? I was going the other way. All right, that's good. You can do that. So subtract 2xy from both sides and you get y equals 3x minus 2xy. Okay, so now what? Factor the x out. Okay, good. So y equals, why is it doing that? Equals, okay. X times 3 minus 2y, and you got one more step to go. Divide by 3 minus 2y. So x equals y divided by 3 minus 2y. Ta-da! Okay? So now, let me think about this. All right, so what does that mean? That means that we have two functions, right? We have, all right, let's go to the next page. We have y as a function of x was what we started with. Y equals 3x over 2x plus 1. And x as the inverse function of y, we got, okay, we got, what the heck did we get? We got y over 3 minus 2y, right? What did we get? Y over 3 minus 2y, yeah, that's what we got. Now, remember, there was an algebraic relationship between inverse functions and there was a graphical relationship, right? If you graph them, what do they look like compared to each other? Remember? Reflection over the line y equals x. Okay, but how are you going to graph this? Y equals 3x plus over 2x plus 1 is easy to graph as y1 in function mode, right? But how are you going to graph x equals y over 3 minus 2y? There's a problem here. We swapped the x's and the y's. We're physically plugging into f inverse, we're physically plugging in the output of f. We're plugging in the y's, right? But that's not how you graph it. If I want to compare these two on the same set of axes, I have to graph y equals 3x over 2x plus 1 and y equals x over 3 minus 2x. Because otherwise you can't graph them on the same set of axes. Right? In other words, in f, the input is x. In f inverse, the input is y. But if you're graphing on the same set of axes, x is the input. So to graph them, to compare them, I'm going to have to switch it around to graphing y equals x over 3 minus 2x, just to see that geometric relationship. Alrighty? So let's do that. Let's graph them. So I'm going to graph these two. But if I'm graphing on the same set of axes, be careful. Here, the input is x. And here, what we're inputting x, but it doesn't mean what the other x means. It means the y, the output from the other function, all right? So this x is really the old y. And this x is really the old y. But I'm doing it this way so I can put them on the same graph paper, right? So how about a zoom 4? So here's y1. And here's y2. Is that a reflection across the line y equals x? Let's see. Y equals x is here. Yep. So this branch reflected down there, and this branch reflected over here. If you want to make it obvious, let's make the inverse function thick. So the thick one should be the reflection of the thin one. Here's the original function, the thin one. Here's the reflection, the thick one. That branch reflected, that branch reflected, across y equals x. So geometrically speaking, it's reflection, yes? How about algebraically? What if I want to compose this function with this function? Okay? So this is what I'm going to say. I'm going to rewrite this. Okay, to graph it, I did this. I did y equals a function of x is what was given. Y equals 3x over 2x plus 1. But now instead of writing x as the inverse function of y, I'm going to say y is the inverse function of x and write down what we graphed. This is what we graphed. All right? Now be careful. That's also an x, sorry. This x is the old y. Don't get confused, all right? The input here is the output from the first equation. So my question to you is this. What's f composed with f inverse? Do you know what it should be? If they are in fact inverse functions? It should cancel out to just plain old x, right? Okay. Let's confirm that. Let's do it. How do you compose these two functions? F of f inverse means take f inverse and plug it into f. Okay, so that's what I'm going to do. F is, all right, so this is what f is. F is 3 times stuff over 2 times stuff plus 1. But the stuff is the f inverse, which is x over 3 minus 2x. X over 3 minus 2x. The question is, does this reduce, in fact, to just plain old x? What do you think? It should, right? Let's see. How do you simplify this mess? What would you do? Distribute the 2, distribute the 3. Okay. So, all right, so let's put it down here. It's going to be, I'm running too big. I'm running out of room here. It's going to be 3x. Wow, I'm really running out of room here. Okay, hang on. All right, it's going to be, you know what? I'm going to write it down somewhere. Where did my paper go that I just had? Here. I just jot this down for a second. It's going to be 3x over 3 minus 2x over 2x over 3 minus 2x quantity plus 1. All right, I ran out of room here, so I'm going to do that on the next page. Okay, so you get 3x over 3 minus 2x over 2x over 3 minus 2x plus 1. All right. Now, we've played around with fractions like this before. How do you simplify this mess? Get a common denominator. Rewrite the 1 as 3 minus 2x over 3 minus 2x. Let's write that. Okay, so get rid of this and write 3 minus 2x over 3 minus 2x. So forget the numerator. Just take a look at the fractions in the denominator. How do you add them? Since you have common denominators, you add the numerators and leave the denominator. So if you add those numerators, what do you get? 3, just 3, okay. So let's write that. So the numerator, I didn't change it. It's 3x over 3 minus 2x. And then the sum of those fractions is 3 over 3 minus 2x. All right, so now how do you divide? That fraction on the bottom, 3 over 3 minus 2x, how do you divide it into the top? Multiply with the reciprocal. All right. So I ran out of room again, so I'm going to put it over here. 3 minus 2x over 3 is the reciprocal, right? Let me get rid of this. Over here, so I don't need this. I don't need that. And so now clearly, what happens? So what happens now? The 3's, this 3 and this 3 cancel, and the 3 minus 2x cancel, and all that's left is exactly what you wanted, the x. Ta-da! Okay, so f of f inverse is in fact x. Is that enough to prove that these are inverses? No. Not only does f of f inverse have to be x, but the f inverse of f has to be x, because composition is not always commutative. In fact, it's basically only commutative here. So I want to show that this is commutative, that if I do it the other way, I also get x. All right, let's do it the other way. All right, so let's see. So we started off with f of x is 3x over 2x plus 1. And the other f of x, quote unquote x, is x over 3 minus 2x. We did f of f inverse. Right, so now we want to do f inverse of f. Okay. So let's redo the same thing, but sort of backwards. So now I want f, what happened? I want f inverse of f. All right, now f inverse is x over 3 minus 2x, right? So it's stuff over 3 minus 2 stuff. But the stuff is f. And what was f? 3x over 2x plus 1. And put that here too. So this is a whole different expression, but this is also reduced to just plain old x. So you tell me what to do. It's almost the same thing. What would you do next? Not yet. You need one fraction over one fraction for that to happen, for the reciprocal to cancel. I can't reciprocate yet. It's not one fraction on the bottom. So do like we did last time. What are you going to do with the 2? At negative 2 on the bottom, what are you going to do with it? Multiply it in, right? So you get negative 6x. What are you going to do with the 3 on the bottom? Get a common denominator, right? Okay, let's do that. So the top is 3x over 2x plus 1. 3x over 2x plus 1. The bottom is, now this is 3 over 1, right? So I'm going to get that negative 6x over 2x plus 1 over here. But how do I get the 2x plus 1 as a denominator under the 3? Simply multiply top and bottom here by what? 2x plus 1. So 2x plus 1 times 3 is 6x plus 3, isn't it? 3 times 2x plus 1 over the 2x plus 1. Alrighty, so now can you subtract? How do you subtract those fractions on the bottom? Subtract the numerators, keep the denominator. Isn't the same thing happening as happened last time? Okay, so, alright, so let me write that. I'm going to write, I get, on the top it's still 3x over 2x plus 1. On the bottom, the 6x's cancel. And you're left with 3 over 2x plus 1. So how do you divide by 3 over 2x plus 1? Just flip it, right? So, you know what? Let me just do that. So this times the reciprocal of what we had. And almost exactly like last time, that's a 3. Dang it. Almost exactly like last time, the 3's cancel, and the 2x plus 1's cancel, and all that's left is x. Ta-da! That's a QED right there. You have to do it both ways. To show that f inverse is in fact the inverse of f, you have to show that f of f inverse is x, and f inverse of f is also x, that it's commutative. Okay? Wow, there's a lot of writing going on. Alrighty, so we know algebraically what it means to be an inverse, that's it. We know geometrically what it means to be an inverse, the reflection property. Alrighty, I think we clobbered 10.2. Alright. So 10.1 was what's a composition, 10.2 is what's an inverse using compositions. Alright, what's 10.3? 10.3 is just like other random combinations of functions, like adding functions, subtracting functions, multiplying functions together, dividing functions together, see what happens, that kind of stuff. So, for example, how about this? What if I combine all these functions together? Let's say 2x times 6x squared minus 2x times x minus 2 to the x plus 1. Right, so I'm combining all these functions. 2 to the x times 6x squared minus 2 to the x times x minus 2 to the x plus 1. Can I solve that equation for its zeros? Can I find the zeros? When is that zero? How do you solve that equation? That's my question. Any idea how you would find all the real roots of x for x in that function? Any ideas? You see any common pattern here? What keeps on repeating? Right? In this term, in this term, and this term, they all have 2 to the x in there somewhere. Now this is 2 to the x. The first term has 2 to the x. The second term has 2 to the x. The third term doesn't have 2 to the x. It has 2 to the x plus 1. How is that related to 2 to the x? What is 2 to the x plus 1 compared to 2 to the x? Are they related? Can I rewrite that in terms of 2 to the x? Well, it's 2 to the x plus 1, right? So what is it? The x1s are being added, right? Isn't there a rule somewhere we come up with a lot that when you multiply stuff, you add the x1s? Remember that stuff? What is that about? When do you add the x1s? When you're multiplying two exponentials or two powers with the same base. So could you write that? Could you rewrite that as a product of two powers of the same base? 2 to the x times 2 to the 1. In other words, 2 times 2 to the x, right? All right, let's rewrite that. Just simplifying a little bit. So I've got 2 to the x times 6x squared minus 2 to the x times x minus 2 to the x times 2, basically. All right, so that actually made it easier to solve. Wait, that 2's bad. Give me a 2. But I still don't know how to solve this for the zeros. How do you find x such that that whole thing equals 0? Well, again, what do you notice in every single term? 2 to the x. So what's your favorite F word? 6 letters. Factor out what? 2 to the x. Okay, so take out 2 to the x. What's left? Because 2 times 2 to the x is 2 to the x plus 1. In other words, isn't that just 2 to the 1? How do you multiply 2 to the x times 2 to the 1? Multiplying two powers of the same base, you add the exponents, right? So that's 2 to the x times 2 to the 1 is 2 to the x plus 1. Right? Just adding the exponents, 2 to the 1. I didn't write 2 to the 1, but it's 2 to the 1, right? Okay. All right, so factor out and what's left? 6x squared minus x. What? That's it? I'm done? Minus 2, okay. Minus 1, why? Well, it's a factor of 2, though. It's 2x times 2, so factoring out 2x, I'm left with 2. All right. So, remember one of the properties of 0. What is it? When two quantities, 2x and this, multiply out to 0, what do you know? When this multiplies times this and gives you 0, what do you know? that one of these guys had to be 0, one or both of them, I don't know which, right? So you set each factor equal to 0, right? So you say, okay, 2 to the x equals 0, or, right, this is how you solve by factoring. You set equal to 0, and then you factor, and set factors equal to 0, right? Or 6x squared minus x minus 2 equals 0. But then be careful, you know about exponentials. When does 2 to the x equal 0? Can you graph it? It's a mother function. Can you graph it in your head? 2 to the x? What does it look like? It has a horizontal asymptote. What is it? It has a horizontal asymptote that doesn't cross ever. It never hits 0, right? So is 2 to the x ever 0? It never hits the x-axis, which is y equals 0. That's impossible. There's no solution here. But what about the other side? 6x squared minus x minus 2. Can you solve that by factoring further? Do you know how to factor tricky tries? There's greatest common factoring. There's difference of two squares factoring. There's regular trinomial factoring. There's tricky trinomial factoring. I call this tricky trinomial factoring because there's a 6 in front of the x squared that I can't GCF. If it was just a 1x squared in front, I could factor normally. Just reverse FOIL. Do you know how to do tricky try? You're looking for two numbers that multiply out to what? Negative. Someone said 6, someone said negative 2, and I don't agree with either of you. Negative 12. Do you know the eyeglass method? You don't know this stuff? Here, wait. Separate page. Let's refresh your memory. 6x squared minus x minus 2. Is that what it was? Yeah. Now, if there wasn't the 6 in front, you would ask yourself, what multiplies out to negative 2 and adds to negative 1? Right? If it was just this, you would say, what multiplies out to negative 2 and adds to negative 1? And what is it? Negative 2 and positive 1, right? Does it negative 2 times 1, is negative 2 times 1 negative 2? We're getting there, yeah. Is negative 2 times 1 negative, oh wait, you can't factor that, can you? Because negative 2 times 1 is not negative 1. You can't factor this one. This is a quadratic formula one. If it said 2 here, I'd be in business. Negative 2 times, no wait, I'm sorry, take that back. Negative 2 times 1 is negative 2, right. Negative 2 plus 1 is negative 1. That's right. So if I'm solving this, it's easy, because it's just doing FOIL backwards. That's easy, because you're just doing FOIL backwards. You're trying to think of, if I FOILed stuff, what do I need to FOIL to get x squared minus x minus 2? This is different. 6x squared minus x minus 2. I do it this way. Let's see if you've done this. I'm looking for an eyeglass product. You ever see the eyeglass thing? That's somebody's eyeglasses. The product of 6 and negative 2. Okay, what is that? Negative 12. But we're still summing to the middle, negative 1. So can you think of two numbers that multiply up to negative 12 and add up to negative 1? Multiplies to negative 12 and add to negative 1. Huh? Negative 4 and 3. So this is what I do. Yeah, really? Do you have to do this every day? In the middle of my screencast? YouTube, sorry. Yeah, I bet you're finished. Go away. All right, so this is what I do. 6x, 6x, and 6, negative 4, positive 3. What did I just do? This is how you do tricky trinomial factoring. You ever do this? It's also known as the master product algorithm. Is that true? Well, let's find out. What happened here was I converted the problem from a non-GCF to a GCF. I can't GCF to 6, can I? It's not a GCF. But isn't there a GCF here? What goes into 6 and 4? 2. What goes into 6 and 3? 3. So let's factor that out. Let's take out, wait, what'd you say goes into 6 and 4? 2. Okay, I heard, okay. So take it out. What's left? 2 into 6x minus 4 leaves 3x minus 2. Now factor out the 2 into 6x plus 3. I'm sorry, the 3. Factor out 3 in the second factor and you get 2x plus 1. All over 6. But the 2 that you factored out and the 3 that you factored out, what's that? 2 times 3 is 6, cancels the 6 in the denominator, and you end up with 3x minus 2 over 2x plus 1. Now, does that work? How can you check that that's right? Foil it out, right? Foil it out, and you should end up with 6x squared minus x minus 2. Let's see. First times first gives you the 6x squared. Last times last gives you the negative 2. But the let's see, the outer product is 3x, and the inner product is negative 4x. That combines to negative 1x. Perfect. Did you ever factor tricky trinomial factors using the master product algorithm like this? That's how it's done. Okay. So what are the factors of the original equation? 3x minus 2 and 2x plus 1. Okay, let's write that. Let's go back to where we were. We were here. So now I get 3x minus 2, because all that stuff was just scratch work, scratch paper, and 2x plus 1. So now what do you do? How do you solve that? You set 3x minus 2 equal to 0. Okay, so let's do that. Bring it down here. Ding, ding. All right, so we got 3x minus 2 equals 0, or 2x minus 1 plus 1 equals 0. So what do you do to the 2? You add it. So 3x equals 2. What do you do with the 3? So x is 2/3. Okay. Over here, what do you do with the 1? Subtract it. 2x equals negative 1. And what do you do with the 2? So x equals negative 1/2. All right, how do we check all this algebra? Can you check these algebra somehow? How? What if we just took this whole equation and graphed it at this side as y1 to see what the zeros are? Okay. So is everyone agreed that our roots are 2/3 and negative 1/2? And that came from the quadratic portion, not from the exponential portion. There's no solution there. So let's graph what? Let's graph this original thing. Look for the zeros on Ziggy. Here we go. So it's 2 to the x. Whoops. Clear, clear, clear. All right, so what was it now? It was 2 to the x times 6x squared minus 2 to the x times x. Whoa, what happened there? What is that? Minus 2 to the x times x. There you go. Okay. Minus 2 to the x plus 1. Minus 2 to the quantity x plus 1. How about a zoom 4? The zoom 4 would include the roots that I got. So I should see 2 roots here somewhere. Whoops. There's 1. There's the other one. Okay. Does it match my solution over here? What was it? Positive 2/3 and negative 1/2? Does it look like that's a negative 1/2 and that's a positive 2/3? Let's find out. Super trace, 0, and whichever one is closest. Well, no, left bound. Okay, so left bound, let's go a little bit before it. Enter, a little bit after it. Enter, and that's supposed to be the negative 1/2. Let's see. Enter again, don't bother to guess. Negative 0.5? Yep. Ooh, exact. Nice. And so the y is 0 when x is negative 0.5, or negative 1/2. Perfect. And super trace 0 again. Let's go over here. This was supposed to be positive 2/3. What's positive 2/3 as a decimal? What should you see here? 0.6666. Okay, so enter. Go to the right. Enter. Enter. 0.6666666666. Yep, and it rounds off. Because it's running out of decimal places, rounds off in the last place. Okay. Goody. So you know how to add and multiply and divide and combine functions other than composition of functions. Great. Alrighty. All right, I think that's it for our YouTube. Okay, YouTube, that was nice seeing you.